Hey guys, so I wanted to try doing some presentations this way and hoping that this will help you with learning new material. So, entropy. This is the first add-on to thermochemistry that we're going to learn about. So, we have already done thermochemistry when we did all of our work with enthalpy, aka delta H, and all of our methods to calculate enthalpy, whether that was through Hess's law, through bond energy, or standard enthalpies of formation. However, the thermodynamics of chemistry is more than just enthalpy because not all of the energy that guides a reaction is rooted in enthalpy. So we're going to add on and talk about entropy and then inevitably what's called Gibbs free energy. Today we're going to focus on entropy. So first of all, with spontaneous reactions, right? What we mean, of course, by spontaneous reactions are reactions that would occur without outside influence, right? They are going to be temperature dependent, and of course, this does not at all dictate how fast they react, aka kinetics. This is all separate thermodynamics, and the likelihood of a reaction occurring is completely separate from how fast it will occur. Right, so that's an example right there in everyday life would be like rusting of a car. It doesn't necessarily happen fast, but it is considered to be a spontaneous reaction because it happens on its own, whether we really want it to or not. Okay, driving force of reactions. We used to, and really what we talk about in our previous chemistry classes is just that enthalpy is the only factor dictating whether the reaction is spontaneous or not. And while enthalpy plays a huge role, it's not the only role that gets played. So we talked about the fact that having a negative delta H is good, meaning that those are the reactions that would be likely to be spontaneous, okay? Because that means the reactants are higher energy than the products, which energy would be going downhill. That's an ideal situation. However, not all exothermic reactions are spontaneous, and we have also found through time that endothermic reactions that exist also could occur spontaneously, right? So both scenarios that don't fit into that very strict exothermic means spontaneous box, we found some exceptions to those rules, okay? Because there is a thermodynamic variable that we have to consider that's called entropy. So it's just that enthalpy is not the only driving force. We have something called entropy as well. So the symbol you'll see for entropy is delta S, and its units are a little different. Notice that they are joules per mole Kelvin. So the reason I'm highlighting this is because we're used to delta H traditionally being reported in kilojoules per mole. So when we go to talk about entropy and enthalpy combining in Gibbs free energy, it'll be important that we make sure we are converting our entropy into kilojoules, because generally speaking, in any table, and the table that I will give and provide for you to use to get a lot of your data from, anywhere you look, they're going to be in joules per mole Kelvin rather than kilojoules. So what is entropy? It's essentially the measure of disorder, chaos, or randomness, okay? What are we talking about here? So less arrangement would mean higher entropy. More arrangement or more locked into order would be less entropy, okay? So the reactions will always favor going to the highest entropy or highest number of possible states, meaning less order is what's favorable in a reaction as opposed to more order, okay? One of the other driving forces now that we're adding in with enthalpy, not only do we want to be exothermic ideally, we also want to be a reaction in order to happen spontaneously that would increase disorder or entropy. Okay. Spontaneous reaction scorecard. Okay, so this is how we're just going to be thinking about what's the good or what's the bad for creating a spontaneous reaction. So we already know about enthalpy. Having a negative delta H is good, right? AKA being exothermic. Entropy is the opposite. For entropy, we're looking to have a delta S that is positive, because what that means is we're increasing the randomness, we're increasing the disorder, okay? And that's what's favorable, aka that's what will lead to a spontaneous reaction. So what are some things that would increase entropy for a reaction? One of those, increasing the number of molecules, okay? AKA a spontaneous reaction is going to have more moles of substances on the product side than the reactant side. So something like where you start with 1 mole on your reactant side, but end up with 3 total moles. And again, when I say moles, think about balancing coefficients on the product side. That would be an increase in entropy, because you're going from 1 mole of reactants to a total of 3 moles of products. Increase in entropy. A very common type of reaction that I'm referring to there is dissolving, because that's always an ionic solid that's breaking apart into 2 or more ions. So there's an immediate increase in entropy in dissolving, because you're breaking apart into more moles, more particles. Okay, another common increase in entropy is phase change, specifically going from solid to liquid to gas. Because going from solid to liquid and liquid to gas, you are creating more disorder, more randomness, right? Solids are a very specific ordered array of molecules and atoms. We start to break down some of that going to liquid, and then that's almost completely gone away by the time we've gone to gas, and all of those particles can move around at their own discretion. So going from solid liquid to gas is always going to be an increase in entropy. Gas being the most disordered, solid being the least disordered. Anything breaking apart into pieces, right? Another common example is a decomposition reaction, because similar to dissolving, you have one reactant breaking into multiple products. And an increase in temperature is going to be another example of increase in entropy, right? Think about what happens on the molecular level when you increase temperature. Increasing temperature means that the particles are going to end up gaining more kinetic energy and are going to be moving around more. More movement means more chaos and disorder, which means more entropy. Okay, the main way we calculate entropy, it's very similar to a methodology that we used for enthalpy calculation. So one of the ways we calculated enthalpy change for a reaction was by using enthalpies of formation. We can do the same exact format with entropies, okay? They're all standard values for all different substances, and then we ultimately find the change for our specific reaction by doing your sum of your total of your products, their entropies of formation minus the reactants, okay? And I'm going to show you an example now, and just so you know, I'm linking in with this assignment for entropy, a link to a really comprehensive list of not only enthalpies of formation, but entropies, and it'll be later used in the following week of Gibbs-free energies. So here's an example reaction. Just like anything we did with enthalpies, it's critical to balance it first, okay? So here it is balanced, because remember, when we use those entropies of formation, you have to identify every substance that's present, plus how many of each there are, okay? So what we would have to do is go to that link and look up the individual entropy of formations for each different substance here. So for SO2, we find that it's 248, O2, 205, NiO, 38, and NiS is 53. And then we're just going to plug them in. We're going to multiply them by their balancing coefficients, and then sum the products, sum the reactants, and subtract that. So you see here my product, 2 times my 248, that's for my SO2, plus 2 times my 38, which was for my NiO, minus the sum of my reactant side, Okay, 2 times 53 represented my NIS, and 3 times the 205 is going to represent the entropy for oxygen. So when we plug this in and do the math, we see that we get a delta S that is negative 49, or excuse me, negative 149. Now, when we calculate that, delta S we obviously found is decreasing, right? It's a negative number. So in that case, when we have to think to ourselves, is that good or bad for the spontaneity of a reaction? Remember, delta S, we want to be positive. Therefore, since this one was decreasing and it was a negative number, that means that that was not favorable for a spontaneous reaction. Why? Spontaneity favors more disorder. A negative delta S means it's becoming more ordered, right? Even conceptually, if you look at that reaction, right, the first thing I talked about was about how many moles there are from reactant to product side. If you look at just the balanced reaction without you actually plugging in the numbers, you should see that there's a total of 5 moles of reactant, right? 2 NIS plus 3 O2, that's a total of 5 on the reactant side, where there's only 4 moles of products. You're going from 5 to 4. That obviously conceptually shows you that you're even becoming more ordered, right? You're always going to favor going into more things, not less. And that is it. So, if you have any questions, don't forget, I am going to be, from here on out, my plan is to be on Google Hangouts at that link in our classroom from 12:30 to 1 Monday through Fridays. But I'm hoping that this helps because I know a lot of you had mentioned that it would be helpful to hear me. So from moving forward, this is something I'm going to be doing, is going through my presentations and talking through them as well for you with any new topic. Also, this is going to be our last new unit of material just because of how AP has changed things with regards to the remote learning. We're not going to have to cover as many units. So after we complete this unit and test on it, we will move into AP review until the test. So hope this was helpful, guys. And let me know if you have any questions.